This video is about operations with radicals. This is an introductory level, but we've already discussed by the time of this topic some things with radicals already, such as multiplying them and dividing them and just some of the basic structure and properties of them. Now, in this context, we're going to discuss another additional property that we'll need, which is this. We can only add or subtract what are called like radicals. Now, like radicals are kind of like terms, which we're used to for algebraic terms being added or subtracted. They have to be like. Well, in the same way, let's discuss how radicals can be like with some examples. Some examples of like radicals could be like the square root of 2 and the square root of 2. Right? Now, like radicals, obviously, in that case, match identically. But then let's look at an unlike pair that might be of a similar type. So how about the square root of 2 and the square root of 3? Notice the difference there, which is that the radicand, the item underneath the square root, does not match with that pair. So in order for radicals to be like, they have to have the same radicand, or you could say the same expression underneath the root symbol. Moving on to another example of like radicals, suppose we had 3 times the square root of 2x and 4 times the square root of 2x. Okay, so now take what we just discussed previously and notice that these examples have the same radicand. They both have a 2x underneath the root symbol here. But in this pair, what's in front of the root is different. So there's a 3 as the coefficient and then a 4 as a coefficient. Well, notice those do not match, and yet these are like. So, in other words, the coefficients of the radicals, the numbers out in front of the roots, do not have to match for them to be like. Let's look across at an example of unlike radicals, though. Suppose we had square root of x and then the cube root of x. So here we're seeing that though the radicands, that is the items of the expressions underneath the roots, do match in these examples, they have just an x, this time it's the index values that don't match. Remember, when there's no index written, you assume it's a 2 for a square root, which the first expression here has. The second one has a 3, this would be a cube root, and obviously everything matches except those, which means for like radicals, the index must match and the radicand must match. That's the summary of all these examples. Okay, now let's do some work understanding that. The first example set says simplify, and our first example is 19 square root of 7 minus 2 square root of 7. Well, the first thing we must discuss is whether these are like radicals or not. And you'll notice they both have the same index, which is blank, which means these are both square roots. So those match. And also the radicands, the items underneath the roots, are both 7. Those match as well. So these actually do qualify as like radicals. And then to combine them, we do the same thing we would do in algebra. If I had 19x minus 2x, we would do the arithmetic with these coefficients, 19 and 2, and then bring the x just along for the ride. Well, same thing with the radicals. So 19 root 7 minus 2 root 7 would be, well, 19 minus 2 is 17, and then the square root of 7 just comes along for the ride. So 17 square root of 7 is our final result. Moving on to the next example, it reads as 8 square root of 3y minus square root of 3y. Now, remember that if there's a blank coefficient, like for this second term, you could imagine there being a 1 in front of that second square root, so that it's 1 square root of 3y that we're subtracting. But notice these are like radicals for the same reasons we've been defining here, and so we can go ahead and do this arithmetic with the coefficients. The 8 minus the 1 is where we look. 8 minus 1 is 7, so we say 7, and then we bring the square root that is like along for the ride, so 7 square root of 3y would be our final result there. And then thirdly, when you see a square root of 3 plus the square root of 3, this is an important distinction. This may look a lot simpler than the previous two examples, and that is true in some ways, but here's why this is an important example. First of all, let's understand that these are like radicals. They both have square roots. The index values are both blank, which means they match. They're both 2 assumed. And then the radicands, the numbers underneath the roots, are the same as well. Like we've been doing, we have to do the arithmetic with the coefficients of these two terms. So notice they're both blank in front, which means you could assume that there's a 1 coefficient in front of each root. So in other words, 1 root 3 plus 1 root 3 would be 2 root 3, which follows the pattern that we've been seeing in these previous two examples. One thing to note about this, when we're adding like radicals, we do not add the radicands. So it is not okay to say that the square root of 3 plus the square root of 3 is the square root of 6. That is not the case. You do not add the radicands together. We simply add the coefficients that are in front of each term that is a radical, as we've been doing in all of these examples. Now, we're going to bring in also some things we learned before in a previous topic about multiplying radicals. And so in this next example, we have the square root of 5, and then after it, a set of parentheses containing the square root of 3 plus square root of 6. Well, like we've done in any expression like this previously, we're going to distribute the square root of 5 inside the parentheses to each of the root terms there. But let's recall how roots get multiplied together. I'll go through very slowly here. The first set would be square root of 5 times the square root of 3. That gets distributed to the first term inside. Then we go to the second. There's a plus sign, so we'll say plus. And then it's square root of 5 times square root of 6. Well, as you'll recall with multiplying radicals, as long as the index is the same, which is the case in all of these, so this is square root of 5 times square root of 3, the invisible index of 2 matches. When that's the case, as we've already seen in previous topics, you multiply by multiplying the radicands together. So 5 times 3 is 15. So we have the square root of 15 for our first term, and then plus the square root of 30 for our second term, the 5 times the 6. So that is a difference, you'll notice, between adding, subtracting, and multiplying radicals. As we just discussed in the previous example, when adding radicals, they simply have to be like radicals, and then you add with the coefficients. Like we saw in example 2, we added the invisible coefficients of 1 and 1 to get the 2. We did not combine the radicands in any way. It's not as though 3 plus 3 was 6. Those just remained, the square root of 3, for that like radical. But when you multiply radicals, you do actually multiply the radicands together, like we saw here. 5 times 3 is 15. 5 times 6 is 30. And so when multiplying, you do consider what the radicands are and multiply them together, as long as the root index values do match. And so square root of 15 plus square root of 30 is where we can stop with that example. Our next example is similar. It is square root of 6 outside of parentheses, which contain square root of 6 minus square root of 2. Well, in the same way, we're going to distribute our outer square root of 6 value inside, like we did previously here. Now, when we do, maybe we can skip a step this time and not write out as much detail as we did in the previous example, because we know what's going to happen. We're going to multiply these radicands together because all these root index values match. These are all square roots. So square root of 6 times square root of 6 would be square root of 6 times 6. In other words, square root of 36. Then we have a minus sign because we're distributing through this. And then we have square root of, well, 6 times 2 would give us a 12. Now, in this example, we can do a little bit of reducing, which we should do. So the square root of 36, of course, is just 6. But then moving on, the square root of 12 can be reduced, as we've seen previously in radicals. 12 is really 4 times 3, which means you can factor 12 in a way that involves a perfect square. 4 is a square number, which means we can reduce this even further. So let's rewrite again to get 6 minus, and then square root of 4 is 2, so that gets reduced. But the square root of 3 doesn't, so it stays underneath the root. So we have 6 minus 2 times the square root of 3. And that will be our final answer for that example. Let's try some more. This time we're going to do a lot of foiling. Okay, yes, FOIL still applies even with radicals. And in these cases we have a bunch of binomial or 2 terms times 2 terms here set up where you have inside this first example the first set of parentheses containing 6 plus the square root of 5, and then that's multiplied by another set of parentheses containing 9 minus 4 square root of 5. So we use the same old FOIL process here that we've been used to for a while. We'll start with first times first. 6 times 9, of course, is 54. Outer times outer would be 6 times the negative 4 square root of 5. So carefully we'll multiply the coefficients, in other words, the numbers in front together. So 6 gets multiplied by the negative 4 to give us a negative 24. And then the square root of 5 just comes along for the ride, right? That is a radical part of that expression or that term, which means it would only combine in multiplication with another radical, but there isn't one with the 6. So we leave it as negative 24 square root of 5. That's outer times outer. Inner times inner in a similar way will be plus 9 times the square root of 5. And then last times last would be minus, and then 4 times the square root of 25. You're multiplying this time what's inside each radical together. 5 times 5 is 25. Let's go ahead and take this a step further. This would be 54 minus, okay, now we have some like terms in the middle here, the negative 24 square root of 5 and the plus 9 square root of 5. We can combine those to get, using the addition and subtraction we have above, they have like radicals. So negative 24 plus 9 would be a negative 15 square root of 5. And then we can keep going. The square root of 25, of course, is just 5 on the end here, so this is really a 4 times 5. And then we can put this all together because you can combine the like terms of 54 and negative 20 that we really have going on here. Of course, that would give us 34, and then we'll keep this as 34 minus 15 square root of 5. Now, those are not like radicals or like terms, because they do not both have the same radical, so we leave it just like it is, 34 minus 15 square root of 5. Let's go on to a next example. This one begins with a first binomial containing square root of 6 plus square root of 3, and then that's multiplied by a second binomial containing square root of 6 plus 5 square root of 3. Using our same old FOIL process on this one, we'll have, let's see, first times first would be square root of 6 times square root of 6. That is square root of 36. Outer times outer would be a plus 5 square root of 18. Inner times inner would be plus square root of 18. And then last times last would be plus 5 times square root of 9. Now, that's just going one pass through everything using the FOIL process. Now let's go ahead and start simplifying. Square root of 36, of course, is just 6. We have like terms in the middle. 5 root 18 plus root 18. Remember, there's an invisible 1 in front of that plain square root of 18, which would make it positive 6 square root of 18, combining those like radicals. And then plus, at the end, we have 5 times 3. Square root of 9 is really 3. Okay, let's keep going with this. We now have 6 plus the 15 at the end. We could make that 21. And then we have this plus 6 square root of 18, but the square root of 18 could be factored where we have a perfect square, right? 18 is really 9 times 2, and the square root of 9 is reducible. So let's go ahead and finish this off as 21 plus, now the square root of 9 turns into 3, which would be multiplied with the 6 to give us 18, and then we keep the square root of 2 that we have at the end there unreduced. So 21 plus 18 square root of 2 would be our final result. Our next example contains another set of binomials being multiplied together. The first one contains square root of 10 minus square root of 7, and we're multiplying that by another set of parentheses containing square root of 10 plus square root of 7. So let's go ahead and follow our same FOIL process for this one. First times first would be square root of 100. Outer times outer would be plus square root of 70. Inner times inner would be minus square root of 70. Okay, and so we're just using all the properties and rules we have built up to this point when we're going through each of these little steps, right? We're just multiplying roots together. Notice, to multiply radicals, they do not need to be like. Right? We're multiplying, as we just did here, a square root of 10 times the square root of 7. Those are not like radicals, which means we wouldn't be able to add them together, but we're multiplying them as part of the FOIL process. Okay, and then last times last would be a minus square root of 49. Okay, and then we can go through and reduce a lot of this. This will be 10 for square root of 100. Then notice we have plus square root of 70 and minus square root of 70. Those would actually cancel each other out. And then at the end we have minus square root of 49, which is just 7. So really this is just a 10 minus 7, or 3. Our next example begins with a set of parentheses containing 4 square root of 5 plus square root of 2, and then that's multiplied by another set containing a 4 square root of 5 minus square root of 2. We'll go through the same foiling process for these, first times first. Okay, let's be careful here. We're multiplying 4 square root of 5 times 4 square root of 5. Well, remember, what is in front of the roots gets multiplied together. So like the 4 times the 4, we're going to multiply together to get 16. But then what's inside the roots will get multiplied together on their own. So we have a square root of 5 times square root of 5. That would be square root of 25. So we don't mix and match here. We multiply what's in front of a root with what's in front of a root, and with what's inside a root with what's inside a root, keeping those items kind of grouped separately. That's first times first. Now, outer times outer will be the 4 root 5 times a negative root 2. So that will be a negative 4. That coefficient of 4 stays out in front. It'd be like 4 times a negative 1, which is the negative 4 we're seeing here. But then underneath the root we'll have 10, because that's the 5 times 2. Those are both underneath these radicals. We can multiply them together. So minus 4 root 10. Inner times inner will be similar but opposite, so plus 4 root 10. And then last times last will be minus square root of 4. Let's go ahead and simplify through this. We have 16 times the square root of 5, which is really, square root of 25, which is really 5. Then we have this minus 4 root 10 and plus 4 root 10, but those will cancel. And then at the end we have this minus square root of 4, which is really a minus 2. We'll go ahead and take this one step further. 16 times 5 is 80. So really you just have 80 minus 2, which is 78. So 78 is our final result there. And lastly, but never least, we have an example here where we have a binomial, a set of parentheses containing the square root of x minus the square root of 11, close parentheses, but then those parentheses are squared. So let's be really careful to recall our important rules involving exponents and these kinds of expressions. It's really good to review the fact that it may be tempting to try to distribute a power like this 2 inside the parentheses across the subtraction sign, but let's remember that's actually not okay to do. So we're going to put a big no with that. You cannot distribute a power across addition or subtraction. This one has subtraction. Rather, what we have to do is write out this expression twice if that's what it's doing, right? This is being squared. That really means it's multiplied by itself. So we're going to write out the square root of x minus the square root of 11 in parentheses times that exact thing, the square root of x minus the square root of 11 in another set of parentheses. And then, guess what? We're going to FOIL this together. So this is the same kind of algebra we've been using to do this kind of expression in the past. It's just now we're throwing roots in with it. So let's see, first times first would be square root of x times square root of x. We can make that the square root of x squared, again multiplying what's underneath each root together. Then we have minus, for outer times outer, this will be minus square root of x times square root of 11. That would be square root of 11x. Again, we're multiplying what's underneath those roots together. Inner times inner, same thing, minus square root of 11x. And then last times last will be positive, and then square root of 11 times square root of 11 would be square root of 121. And then we can take this up a step further. Now, the square root of x squared has a little bit of complications to it that are actually beyond the scope of this video. This is more of an introductory topic on roots and radicals. In some more advanced topics, you will see me use another rule that you would pull out when dealing with something like the square root of x squared. For now, we're simply going to call that x, okay? Meaning the square root and the square would be like opposite operations that would simply cancel each other out. And there's a little more to that eventually, but for now, we're just calling that x. In the middle, we'll notice we have some like terms. When you have negative square root of x, negative square root of 11x minus square root of 11x, we're going to combine those as like radicals. So again, review above in this video to recall that they do qualify as like radicals. Therefore, we do the math with their coefficients. So this is going to be negative 2 square root of 11x. That's like a negative 1 and negative 1 combined to get the negative 2. A lot of that being part of what we reviewed above. And then lastly, the square root of 121 is just 11. So altogether we have x minus 2 square root of 11x minus 11 as our final results.